This week we will talk about ocean chemistry. We will focus on the dissolved solids in the ocean, but we will also talk about measuring salinity and dissolved gases and a few other characteristics. So salt in solution, we usually think of sodium and chlorine, sodium chloride, salt water. We will see that in seawater there's a lot more than sodium and chloride. The reason I like this particular portion of the figure from your book is it shows you how water works as a solvent. So remember back to the previous chapter when we talked about water molecules having that Mickey Mouse shape where the ears have a positive charge and the chin has a negative charge. You can see that with a mineral like sodium chloride, the sodiums and the chlorides get pulled toward the opposite ends of the water molecule, so they can actually pull sodium chloride apart. Now, it's very important to understand that the sodium and chlorine in the seawater that we look at is not coming primarily or much at all from somebody shaking salt into the ocean. So we'll find out where the sodium and the chloride come from. That's one of the little interesting points when we look at seawater, because they actually come from different sources. So just some general notes on seawater. The salinity is the measure of dissolved inorganic solids. So it's also called total dissolved solids. The average seawater salinity is about 3.5%. Your book and oceanographers very often use parts per thousand. And you'll notice right next to the 3.5% in parentheses is 35 and then kind of a weird looking percent sign. That's actually the sign for parts per thousand. Percent technically is parts per hundred, and this notation in parentheses is parts per thousand. So you can see we go from percent to parts per thousand just by moving the decimal point one to the right. But I'm going to, generally speaking, stick with percent just so you can see how these numbers relate to each other. The actual salinity of seawater can vary between roughly 3.3 and 3.7%. And in some coastal regions, especially if you get up into what we call an estuary, which is a place where freshwater and seawater mix, you can get lower numbers than that. But that's technically not out in the ocean. The other thing to note, and we'll mention this again on another slide, is that the ratio of most of the dissolved solids in the ocean is constant. So the proportion of each dissolved ion with respect to the other dissolved ions is relatively constant, and that actually makes our job of measuring the salinity in any one location and knowing what's dissolved in it relatively simple. Where do these dissolved solids come from? They come from three primary sources: weathering of surface rocks, outgassing from volcanoes, and from living organisms. And this will be our sources for dissolved gases as well, although really our dissolved gases are primarily coming in from the atmosphere. So we won't worry about sources of dissolved gases too much. So something to remember is with increasing salinity, so as the seawater gets saltier, the heat capacity decreases, the freezing point decreases, evaporation slows down, the density of the water increases, and something called osmotic pressure increases. And osmotic pressure, that's kind of a placeholder. We are going to talk about that later in the semester when we talk about life in the ocean. So the osmotic pressure is going to be important, but it's going to be important when we get to life in the ocean, which is toward the end of the semester. So what do we see when we actually look in seawater? So salinity, that 3.5%, and you can see here it's actually, that's kind of rounded off. So water, in 1 kilogram of water, you can see mostly water, but we've got 3.5% or 34.4 grams in a 1,000 gram sample, or 1 kilogram of seawater, is dissolved components. So It's not 100% water. It is 96.5% water and then 3.5% dissolved solids. And you can see of those dissolved materials in the pie chart, most of it is the chloride ion. In second place is sodium. That's why it tastes salty. And then you can see the other ions listed here as well. Sulfate is number 3. That is why seawater smells a little bit sulfury. Magnesium, bicarbonate, calcium, and potassium. And we have a table right here where I brought in some important information. So that's why I put it on this table here. One of the things I like to do when we're face-to-face in the classroom is have students kind of speculate, where do these components come from? So up here at the top, of course, we have water, 96.5% water. That just comes from the hydrologic cycle, which is highlighted at the beginning of chapter 7. And then we get into the dissolved solids. Very interesting to note here that the chloride comes primarily from volcanic vents, while the sodium comes primarily from weathering of rocks. So you'll notice nobody's dumping salt into the ocean. The sodium and the chlorine are coming from two different places. You can see the sulfate comes primarily from volcanic vents, magnesium from the rocks. So we're kind of going back and forth. The calcium that we find in the seawater comes from rocks and life. The potassium comes primarily from rocks, and the bicarbonate ion, which is this HCO3, comes from volcanic vents and from life and from rocks. It's got a bunch of sources. The other number to note over here is the residence time, and this is how much time an average ion spends in the ocean before it comes out of solution. And you'll notice that the chlorine is in there for a long time, 100 million years, sodium as well. And the reason for that is there aren't a lot of biological processes or chemical processes that will remove these substances from the ocean. However, as far as we can tell, the processes that add these substances and the processes that remove them are in balance, and this is an average amount of time that each of those substances spends in seawater. You'll notice that the bicarbonate ion, which is very often used by life, and calcium, which is also used by life to make shells, they put those two together to make a calcium carbonate shell. Because life is pulling those things out of the water, they have shorter residence times. If we get down here below the black line, these are the minor constituents dissolved in seawater. And I put a few on there just for they have special interest. Silicon is used by a very small number of organisms to make their shells. We talked about that with marine sediments and the siliceous ooze. So there are some microscopic organisms that use silicon in their shells. Iron is kind of interesting. It's got a very, very short residence time because as soon as iron encounters oxygen, it will form a solid iron oxide and settle out. And so this is an example of something with a really short residence time because there's a quick chemical reaction that will pull it back out of the water. Nitrogen and phosphorus, we don't have residence times there. The main reason I put those on there is that they are very, very important nutrients for life in the ocean. And life adds these two, but it also, humans are responsible for adding these as well. They are in short supply in the ocean. You can see the concentration of each of those is quite low, but they are important fertilizers for photosynthetic organisms. So when human activity adds nitrogen and phosphorus to the ocean, we actually see a bloom of photosynthetic life. And then I put the gold down there just for fun. In your textbook, it converts these numbers into parts per million and parts per billion. I put them into percent so you could just see how very little of those substances is actually present in the water, in seawater, compared to these things that are up above the black line or at the top of the list. so the significant components. This is a table from your book that highlights the residence time. One of the principles of the ocean is the principle of constant proportions. And what we discover is that when we take a sample of seawater to measure its salinity, many of these components are in constant proportion to each other. So as the percent of any of these components on the left goes up or down, we will see the percent of all of them go up and down. And what that means is these numbers right here are when we're at the average salinity of 3.5%. But let's say we went up to 3.6 or 3.7, or down to 3.4 or 3.3, we would see all of these primary components going up and down together in constant proportions. So that's what this means. And the reason for that is that the processes that are adding them and removing them are in balance, and their residence time is pretty long. So you can see hundreds of millions of years. The mixing time for the ocean. So we will be talking in the future about ocean currents, but the oceans are constantly being mixed by currents. And the mixing time for the ocean is roughly 1,600 years or 1,600 years. Any dissolved material that's in the ocean for longer than 1,600 years should be in constant proportion, because 1,600 years is the time it takes us to basically completely mix the ocean. So if something has a residence time of longer than 1,600 years, it should be evenly mixed throughout the ocean. And so on this chart, you'll notice that the bottom three, manganese is very close to that mixing time, but things like aluminum and iron are much lower, and so we would not expect them to be evenly mixed. The water should be fairly evenly mixed throughout the ocean, and you would say, well, water is water, and that's what the ocean is made of. But there are variations in some of the isotopes of oxygen and hydrogen that we find in water, and we would expect all of those slightly different types of water that have different isotopes in them to be evenly mixed in the ocean as well. So that's the principle of constant proportions. How do we measure salinity? Well, up here at the top of the slide, it says evaporate the water, weigh the remaining precipitates. So when you evaporate the water, these dissolved solids will start to bond to each other and form solid crystalline substances, which are chemical precipitates. They will settle out of the water, and you can weigh them, and that's kind of the easy, simple way to measure salinity. This is not the most precise way because some of the components evaporate. If you look back here, we don't have an equal quantity, equal proportion of sodium and chloride, for example. So we just can't precipitate out salt. The remaining chlorides are going to have to bond with something else, which some of them do. But chloride can also turn into chlorine gas and vaporize into the atmosphere. So if you do this little technique, it is imprecise. Because of the principle of constant proportions, you could just do a chemical analysis to see how much chlorine is present, and then you do a little math and you can calculate the rest. So that's the second way to do it if you have a chemistry lab. The easy way to do it, and to do this out in the field, is to just measure the electrical conductivity of the water. You'll notice that these are ions. They have positive and negative charges. So their presence is what makes or allows water to conduct electricity. Pure water does not conduct electricity, and the more dissolved ions you add, the greater the conductivity will be. And so because of that relationship, you can measure the salinity of the ocean using the conductivity of the water sample.